Test the series, the sum from n equals 1 to infinity of 1 over 2 to the n plus 1 for convergence. So we look at this and we're looking, well, can we set up some kind of comparison test? Can we find something that will converge and we know is bigger than it for the domain we're interested in? So for something like this, you're looking, when you're trying to compare something that does converge, you're looking for a convergent geometric series, a geometric series where the common ratio is, where the absolute value of the common ratio is less than 1, or you're looking for a p-series, which is 1 over x to the p, where p is greater than 1. In this case, we're looking to aim at a geometric series, which is going to end up being a half to the power n, so common ratio of a half, right? So the way we do that, we start with basic number facts. It's high level stuff, this, but it's amazing how many sort of really basic facts you use just to state your argument. So for the domain we're interested in, which is a positive integer n, 2 to the n plus 1, well, that is always going to be greater than 2 to the n, because it's just 2 to the n, then you add on 1, it's always going to be exactly 1 greater. And actually, it's always going to be positive. It's always positive. For positive integer n. Now, it doesn't matter if it's positive in other places too. It's just we're only considering positive integer n, so it's no problem just keeping writing it. That is the domain we are interested in. Okay, so now, to make it look like what we actually want it to look like, which is this 1 over 2 to the n plus 1, we're going to take the reciprocal of both of these things. So of the 2 to the n plus 1 and the 2 to the n. So that must mean that 1 over 2 to the n plus 1, well, if 2 to the n plus 1 is bigger than 2 to the n, then when we divide 1 by it, if we divide 1 by something bigger, and we know everything's positive, then that's going to make something smaller. So that is going to be less than 1 over 2 to the n, and we just said that everything was positive, so we know that both of these things must be greater than 0. And now, just in exactly the same way as we did this for improper integrals, you have got something set up where you can use a comparison test. So you've got two different series or sequences, which we will think of in terms of series. They're both positive, and one is bigger than the other over the whole of the domain. Or positive integer n. Okay, so if the big one converges, then the small one will converge as well. And if the small one diverges, the big one will diverge. So we're looking to show that the small one converges. So that means we're hoping that the bigger one is going to converge, this series. So basically 1 over 2 to the n equals, well, you could think of that as 1 to the n over 2 to the n. Because 1 to the n is just 1 anyway. So that is exactly the same as 1 over 2 to the power n, just using simple power rules. Okay, so now we know that if we can put that in the form of a series, so the sum from n equals 1 to infinity of 1/2 to the n, we know that that converges. And the reason it converges is because it is a geometric series with the common ratio, or the absolute value of the common ratio, less than 1. So those terms just die off. We know when we have a situation like that, you can use the sum to infinity formula, which means obviously it converges. We could work out what it converges to, but it's not going to help us in this question. Okay, so if that converges, then looking at that, it must mean that this converges as well because of the comparison test. So therefore, the sum from n equals 1 to infinity of 1 over 2 to the n plus 1 converges as well. And converges also. Need to state the reason. The reason is the comparison test. Okay, and that one's finished.